Hi everyone. Today we'll look at redundant connection problem. So we are given a tree with one problem. That is, the tree has one more connection that makes a cycle in the tree. And we have to find out what that connection is and return the answer. For example, we have this tree. It's supposed to be a tree, but there is one extra connection, which is 2, 3. If we remove this, it becomes a tree. If we have this, there is a cycle in this tree, right? So that is what we need to identify and give it as the output. Let's take this example, right? So if we remove this 1, 4, it becomes a tree. It can be a straight line, right? It is a tree. If we add this, then we have a cycle. So we'll have to find out what that last edge that forms a cycle is. So if in this cycle, right, we can remove any of the 4 edges to make it back to a tree. But what is expected from us is of this list, right, of these 4 edges, whichever comes last, right, that should be our output. So this is the question. So to understand this, we need this union find algorithm. We will see how it is. So here union find is a algorithm and a data structure in itself. Okay, so this graph, this input is, what you see here is a data structure, a graph in itself, but we are using this as a data structure in itself that is related to the graph that we have. Okay, so what is union find? It is basically two functions, a find function and a union function. See, let's say we know only what nodes are there and we are constructing this graph based on the edges one by one. Okay, so we we are in the we connected 1 and 2 here, and after that we see 3 and 4, we connected this, right? Now as long as there are no connections between these two groups, these are two separate groups, right? At this point, if these two functions, let's say if I want to see if node 1 is part of which group and node 4 it's part of which group, right? So it will be two separate groups. So the identification of which group a node belongs to, that the find function will do. We'll look at the code later. Okay, the union function is to connect two groups and call it one. Let's say we discover that this 3 and 1 is the next edge. Okay, so this 3 and 1 are next edge. It means they are supposed to be the same group. So the union function, if we call, it will become the same group. Okay, if you see in this data structure, it used to be like two separate groups. Now it has become one group. Okay, so these are the two functions in union find. How is it relevant for our problem? We'll see that. If we take a binary tree and construct these edges one by one, each node is a separate group, let's imagine, and there are no lines. Now if we draw these lines one by one, whenever we are going to draw a line to a group in itself, right, let's say it's between 2 to 6 or 2 to 9 or like 5 to 9, anything, right? Whenever we draw a line between two nodes in the same group, when the tree is being constructed and we draw a line, then that means there is a loop in the program, and we'll have to return what is the last line that we drew. Okay, so that is where this union find helps us. So as we discover these edges, we will keep drawing those lines and seeing we'll first see whether those two nodes are part of the same group. Let's say this 3 and 1, right? So before we encounter 3 and 1, we will see whether these 3 and 1, we'll do a find to see if they are part of different groups. And once we know that they are part of different groups, then we'll make the connection and say that they are part of the same group now. So we keep doing this till we find a line that is part of the same group. Okay, so now we came to 2, 4, sorry, the 4, 2, right? So this 4 and 2 are part of the same group at this point. So that is when we identify that this is the line that forms the last edge in the loop. Okay, where is the loop, you can ask. If you tilt your head towards the right, you can see like an infinity sign, right? So that is the loop. So let me restart the program. Okay, so the algorithm is that we go each edge, right? So when we start out, each node is a group in itself. Okay, each node, its parent is itself. Okay, so that is what this data structure here implies. So each node we have like, one value here. And then for each node, what is its parent? Its parent is itself. Okay, now we discover the edges one by one. Okay, 2 comma 1. So we like find that they are two different groups. Okay, we first run a find for both of these. We identify that they are two different groups. Then we do a union and merge these two into one group. And after that, we do this edge. They are two separate groups. We merge them and make them one group. And after that, we discover that there are like these two groups, right? 1 and 3 are two different groups. Now we merge them, but there is, like this is when we will introduce this concept called rank. Okay, so the rank is like, the weightage, the size of a particular group, right? And if a group, a node has a higher rank, that will become the parent, and the node that has the lower rank will become the child. Okay, so in this example, this 3 has a rank of 2. Okay, whereas this 1 that we are going to connect has a rank of 1, which means 3 will become the parent and 1 will become the child. Okay, but we are not connecting 1 and 3 directly. We are connecting the roots of the groups together. So this becomes 3, 2, 1. Okay, so next we discover 5 and 1. So at this point, what will happen is we will like, have 5 as the child of this group 3, but between that we do one more step. What we do is called a path compression, right? So what was 1, 2, and 3, now instead of like, going from 1, 2 and discovering the root 3, we will do a path compression and make 1 a direct child of 3. Why are we doing this? So the identity for the group is the root node. And that is all we care about when we do a find. So like, when we are like, doing the find between 1 and 5, right? Whether these two are like, separate groups, how we will identify whether they are separate groups is to see what the root is for these two groups. So if I want to see what is the root for 1, I'll go to 1, look at its parent and look at its parent, right? And that is what I'll be like jumping through this parent array and find that the parent is 3. And here I'll find that the parent for 5 is 5. Okay, so for 1 it is a 2 and for 2 it is 3, right? So it is 1, 2, 3. That jump happens here. Okay, so now for 5 it is just 5. Now instead of like, having these jumps and delaying the find, when I identify an opportunity, I will do a path compression and say 1 is a direct child of 3. So this is like, because we care only about the root node, like, we don't care about the height. And if the height is reduced, we can do the find even quicker. So we do something called path compression here. Okay, now 1 and 5, we have to, make them as part of the same group. They both share the same root node. Okay, so we keep going like this. Next we do 6 and 2, we merge it into the same group. And then 7 and 5, we merge it into the same group. 3 and 8, again they are two separate groups. We do a find and we do a union. Now the next edge, 4 and 2, if you look at these yellow circles, they both are in the same group, which means we have identified the last edge in the cycle. Okay, so and that is the answer we will return. So does this mean that like, the node has to be always, at the tail end? It is not necessary. For example, this 7 and 5, right? Even if it comes, later, let me cut this and paste it here, right? Now, the 7 and 5 comes at the end and it is unrelated to our cycle. Okay, but if you look at it, before even we connect this 7, 5, we've identified where the loop is and what is the last edge in the loop. Okay, now that we have a fair idea on how this data structure works, right, we will go into the code, we will understand better. So to do our union find, we need this data structure. One is the parent list. So at the beginning, as we saw, each node is the parent of itself. So what we do, we just do the range, like, one for one, the parent is one, for two, the parent is two, like that. Okay. The next thing that we do is initialize the rank. Each node has only this default rank of 1. As more children get added to that particular group, right? So the rank will increase for those nodes. Okay. So find, what will it do? It will have to go traverse the list, traverse this data structure, and find what is the topmost parent for a particular node. For example, as we saw, when it was this, right? When it was 1, 2, 3, the find function, when we are querying for 1, it will return 3. How does it do it? We see here, right? While the parent of x is not itself, it will keep going, right? Once it reaches 3, 3 is the parent of itself because that is the top node, and that is what will be the answer. So here for 1, node 1, the parent is 2. So we go to 2. For 2, the parent is 3. We go to 3. For 3, the parent is 3. It is the parent of itself. So we return that as an answer. But in the meanwhile, we also do this thing called path compression, right? What do? We do parent of x equals parent of x, which means, here, instead of having 2 as a parent, right, we will have 1 as the parent here. Sorry, 3 as the parent here. Previously it was 2. If you see, for 1, the parent was 2. Now it has changed to 3 here. Okay, so this path compression, next time we query 1 and see what its parent is, we don't have to go in circles. We'll just, the number of cycles for find will just be like these 2. It'll find the parent, and after that it'll see like, okay, it's a parent of itself, so it'll return. So this is the find function. Now let's go to union. Union is where we will say this is the root of a node, this is the root of the other node. Now union and make it into one group. Now what will, if we want to union, what will we do? We'll have to make the parent of those two nodes the same. Okay, we do that by seeing the rank. Okay, this is where rank comes in. Okay, so root A and root B. Okay, if the root A rank is lesser than root B, then root A becomes the child and root B becomes the parent. If it is not so, it is the other way around. So why do we need this? Again, this is so that this find function does not have a really high height, so that this find and union or our life becomes easy by having as less hops as possible in the recursion. So this is how union find works. Now, there is one last thing that we'll see, right? So we are asked to return the last one, right? So of these 4 edges in the cycle, we are asked to return what comes at the end of this list that we are given, right? So what if what if there is another edge that we should return of these 4? How do we know that we are returning what comes last in the list? So whenever you identify that this line is actually creating the loop, then that is by default the last line, right? So if you look at this binary tree example, we keep constructing the tree. Whenever there is a line that goes and forms the loop, that is by default the last, and that is what we will return. Okay, so to try out these simulations, you can go to happme.dev. Sorry, I'm in the dev pre-prod branch, but it should work in happme.dev as well. So please do try out these. If you have any further doubts and clarifications, or if you want to learn this more or try out new inputs, please do. So thank you. See you in the next video.